So let's start with the next topic. It is the potential energy of a spring. So it is a question that show that the elastic force of a spring is a conservative force. So whatever the elastic force that is hand in the spring is a conservative force. Hence, write an expression for the potential energy of an elastic stretched spring. So we have to write an expression. What is the potential energy of an elastic stretched spring? Okay. So let's say potential energy of a spring. First, find what is the potential energy of an spring. So let's consider an elastic spring. So this is a elastic spring which is attached to a rigid support. So this is a rigid support. It is attached to the rigid support. Its other end is attached to a block of mass m. This is a block with mass m which can slide over a smooth horizontal surface. So surface is smooth, which means friction force is zero. Okay. So the position x is equals to 0. So this is the mean position. It is a mean position. At mean position, the x is 0. It is the equilibrium position or mean position or equilibrium position. When the spring is stretched, so when we stretch this spring or compress the spring by pulling or pushing the block, a spring force Fs begins to act in the spring towards the equilibrium position. Okay, so this spring force wants to bring this block towards wants to maintain this block at the equilibrium position. So if we pull this block away from this equilibrium position, this force will act towards the equilibrium position. And also if we compress this block, this force again act towards the equilibrium position. So we take sign convention that x is positive because it is in positive x direction and fs is in the negative x direction, so it is negative. Here both are zero. There is no spring force and displacement is also zero at equilibrium position. And here the direction of force is positive whereas the displacement is negative. So equilibrium, stretch and compressed states of an elastic spring. Now let's apply Hooke's law. So what is the Hooke's law? Hooke's law states that the spring force is directly proportional to displacement. So the spring force Fs is proportional to the displacement of the block from the equilibrium position. So displacement of block from equilibrium position. So it is directly proportional. And when we remove this proportionality sign, so it is coming as minus k. So spring force is equals to minus kx. The proportionality constant k is called as the spring constant. So this k is called as the spring constant. Its SI unit is Newton per meter. So k SI unit of k is Newton per meter. The spring is stiff if k is larger. So if k is larger, which means what? Spring is stiff. And spring is soft is k is small. K is small, which means what? Spring is soft. So the negative sign of Fs. So this is the negative sign which shows that the Fs acts in the opposite direction to x. Means Fs and x both are always in opposite direction. We can see here if Fs is positive, x is negative. If Fs is negative, x is positive, which means they both are in the opposite direction. So therefore this force is always negative if we consider the sign convention. Then the work done by the spring force for a small extension. Let's say we are taking only just a small extension. Let's say there is a spring. This there here there is x is equals to 0. So we are stretching this from this position to this position. Very small extension. It is very small. So dx. So for very small extension, we are applying this force. We can't apply this force for the whole extension because we know that the spring force is variable. Why it is variable? Because it depends on the, it is directly proportional to x. So as the x is variable, so the spring force is also variable, it is not constant. So here we have to use integration. So for integration, first of all, for integration we have to find the small work done. So small work done is equals to fs into dx. Then we put the value of fs, it is minus kx dx. Then if the block is moved from an initial displacement xi, let's say the initial position, it is block is moving, let's say xi to x final, its final position, then we know that we can write work done like this, x initial to x final, and we put the value of this dw integration. So then we, if we solve this, so this k comes out, then x integration x become x square by 2. So this become our formula, that half kx I square minus half kx f square. So if the block is pulled from xi and allowed to return to xi, what we are taking? We are taking that the if the block is we are pulling the block from xi and again it will return to the xi, which means displacement will become 0. So this limit becomes same, this x final is also equal to the x initial. So if you put this limit, so this becomes 0, which means there is no work. So the above discussion shows that the spring force is position dependent as it clears in the Hooke's law. So we can say that spring force depends on the position. It is directly proportional to displacement. Next thing is the work done by the spring force depend on the initial and final position. Okay. So we know if the work done depends on the initial and final position, which means what? It is conservative force, because we know because of the conservative force only the work done depends only on the initial and final points or other end points. Okay. And the third point is the work done by the spring force in cycling process is zero. That we prove that if it is process is cyclic, that x f become x initial, then work done will become zero. So this satisfy this all condition that the work done by the spring force in cycling process is zero. Thus the spring force is a conservative force. Remember when this follow this all three these two conditions, it depends on the endpoints, and second is the closed process is zero, then the force is called as the conservative force. In order to pull the block outwards with a slow constant speed, an external force F equal and opposite to Fs. So as per Newton's third law, the spring force is equal and opposite to the applied force. So the work done by the external force, if we find work done by the external force, will be equal to the increase in potential energy of the spring and is given by. So what are the work done? Work done equal to increase in potential energy. So as we pull the spring, so spring get stored the potential energy. So work done is equals to change in the potential energy. External force will be equal to increase in whatever the increase in potential energy. So how to find increase? Increase is the final minus initial. So by final minus initial, we can find the whatever the total energy in current potential energy increases. So that will become our work done. I mean that work done we have to do. Okay. If we are stretching spring from initial position, let's say initial xi to x final. So if you want to find what the work done we do by an applied force, so this work done will equal to increase in potential energy. How much potential energy increases, that is equal to the work done. So this become work done. Okay. Now if we take the potential energy ux of a spring to be zero when the block is in equilibrium position. Okay. So at equilibrium, what we take? We know that at equilibrium, we took potential energy is zero. So the potential energy of the spring for an example at x will be, so we can write it like this, u x minus 0. Okay, if at x position the potential energy is at point x, what is the potential energy? It become half kx square, and at equilibrium it is 0. So if we find the change from x to 0, x to equilibrium, so this will become u at any point x is half kx square. I mean if we put in this value, if we put in this value that the final position is x and the initial position is 0, so if we put the value in this position, so this becomes ux minus 0, so we got the value of potential energy, it is half kx square. Now next question is draw a plot of spring force fs and the displacement x. So we want to draw this plot, hence find the expression for potential energy of an elastically stretched spring. So potential energy of an elastic stretch spring by a graphical method. Now we have to prove this by a graphical method. So here we draw a plot of the spring force and the displacement, and to find the spring force versus the x plot, and we want to show the uh, potential energy. So we know potential energy is what? Potential energy is half kx square. So if we write in terms of fs and x, so this become half kx into x. So this become half into fs spring force into x. So this become our potential energy. So we know for this, this is like this. This is the formula of a triangle. So on this plot, we got a triangle. So if we take, if we stretch the spring, so x become positive and this force become negative. If we stretch the spring, let's say there is an equilibrium position, and if we stretch this, so the spring force in the negative direction and the displacement in this direction. So let's say displacement is xm, the maximum displacement is xm, and the force is negative. So this force is negative minus fs, or force is negative. So this triangle, okay, and this, uh, so if we plot this two, and if we match from starting from 0, so we got this triangle. So this triangle gives us the this uh, potential energy. If you find its value, it comes at half fs into x. And if we compress the spring, then in case of compression, fs is positive and x is negative. So this come at this side. If we compress this, if we take for the compression, so here xm will come, and here the fs will come. Fs is positive. So if we plot this curve, so we got here also half kx square, kxm square. So this is for the compression, this is for the case of compression, and this is for the case of expansion. So this is our plot, and now according to Hooke's law, we know that spring force is equals to minus k into x. So here spring force for an extension, let's say we took an extension of xm. So this become our extension. Now the work done by the spring force for an extension xm is, so it is equal to area of OBA. So this OBA, this area will give us the work done. So we know that what is the work done. I told you that if you want to find the work done by a variable force, so I told you that the area under force displacement curve will give you the work done. So therefore here we find the area under this force displacement curve. So it's become half into fs into xm, and if we put the value of fs, so fs value of fs is minus kxm. So this become minus half into kxm square. This we got the our work done. In order to stretch the spring slowly, an external force F equals to an opposite to Fs. Okay. So if you want to pull this, stop this block, let's say here is the mean position, and if we stretch this spring from here to here, and if we want to, there is a spring force. So to stop at this position, we have to apply and some external force which is equal and opposite to Fs. So to external force equal and opposite to Fs has to be applied. So the work done by the external force. So if you want to find this is an external force. So the work done by external force, so it will give the same work done. Just because this from here the force is positive, so the work done will get as the positive. So this become negative of the spring force. So this become half kxm square. So work done due to the external force is positive, and work done due to the spring force is negative. As here you can see, this is work done due to spring force, okay, of an extension. So work done due to spring force is negative, and work done due to the external force is positive. So the work done is stored as the potential energy. So whatever the work done we do, to stress the spring, it getting stored in terms of the potential energy of the spring. So this is the work done. So this is the work done we do to pull this block, to stress this block, or to stress the spring. So this get stored in terms of potential energy. So this we show that the work done is equals to potential energy. Now next question is, so that the total energy of the stretch spring remain conserved. So if we stretch a spring, so we have to prove that the total energy remain conserved, okay, when it is released. Find the expression for the maximum speed. That what is the maximum speed when this block is getting released after stretching. So next thing is, show that the total energy conserve. Okay, so conservation of energy in an elastic spring. So if we stretch a spring to a distance, let's say xm, its potential energy, we find that its potential energy will become half kxm square. The potential energy get stored in the spring. So when it is released, so when we release it, so it begins to move under the spring force. Because of the spring force, it begins to move towards the equilibrium position till it reaches the equilibrium position where x is equals to 0. So where it has maximum velocity. Okay. So at position x is equals to 0, what happened? The potential energy will become 0. So the all this potential energy will get manifested into kinetic energy. So at equilibrium position, it has maximum velocity because kinetic energy is maximum at equilibrium position. So all the potential energy is converted into kinetic energy due to the inertia of motion. Is the inertia in the motion? So the body overshoots the x is equals to 0 position. And because of the inertia, there is an inertia in the body. So because it overshoots the equilibrium position, x is equals to 0 position, and it get compressed, spring get compressed. So its velocity decreases until its movement entirely stops. Okay, momentarily stops. So it stops at the x is equals to minus xm position. So what is happening here? We have a spring. There is an equilibrium position. It is x is equals to 0. We are stretching this spring up to here xm, and we are releasing this spring. So when we are releasing, so this block is not stopping at the equilibrium position. This is stopping at this position, which is x is equals to minus xm, because of the inertia of the body, inertia of this block. So at this position, what happened if it get stopped? It get stopped at this position. At this position, it get stopped. So if it get stopped, its velocity becomes 0. So where the all the kinetic energy is converted again into the potential energy at this position. So the spring force again pulls the body towards the x equals to 0. So now it again regain the potential energy. When it reaches to x is equals to minus xn, it will again store some potential energy. Then the spring force again pushes it towards the this point equilibrium position. So thus the body keeps on oscillating from minus xm to plus xm. So the total mechanical energy remains constant. It will just manifest itself. So now let's take some extreme point at an extreme position. So first let's take x is equals to plus xm and minus xm. So at this position, what happened? Body get stopped for an instance, for a very small time, for an instance. So if for an instance the velocity will become 0. So if velocity becomes 0, kinetic energy will become 0, which means all the energy which it possesses, the spring possesses the potential energy, and which is equal to half kxm square. It's the maximum value of the potential energy. Now at any extreme position x, okay, so we are taking it any extreme position, any position between minus xm and plus xm, and we find the energy is so at any position, so energy is partly kinetic and partly potential. At extreme, kinetic energy is 0, and at equilibrium potential energy is 0. But if we took any point between these extremes, at x is equals to plus minus xm or at x is equals to 0, so where the energy is partly kinetic and partly potential. So we know total energy is sum of kinetic and potential. So total energy is we take as the half. We are equating this energy. So we know total energy remain conserved. So we are equating total energy at extreme position at x is equals to xm, plus minus xm, x is equals to plus minus xm. So this we are equating this energy with energy at any position x. So this is the position x. So we know at x is equals to xm, total energy is half kxm square. Why? Because at extreme position kinetic energy is zero, because there the velocity is zero. And if you want to find the total energy, so this become total energy at the extreme position. And if you want to find the total energy at extreme, so it is a sum of kinetic plus potential energy. So kinetic will become half mv square, potential will become half kx square. So if we took like kinetic energy is equals to half mv square. So if we took kinetic energy is equals to, so if we send this towards this side, so this become half k xm square minus x square. Now from here we can find the value of the velocity. That what is the velocity? So from here we get the value of velocity. Now let's put some equation. So at equilibrium position, what happened? X becomes zero. So if x becomes zero, so this velocity will become zero. I told you at x is equals to zero. What happened? This the potential energy, not this uh, x is equals to zero. Potential energy will become zero because it is half kxm square. So x becomes zero. This potential energy will become zero. So all this energy is getting converted into kinetic energy. So at x is equals to 0, we have maximum velocity because all the potential energy getting converted into kinetic energy. So kinetic energy is maximum at x is equals to 0. It is maximum. So velocity is also maximum. So at this position we write Vm. And we know the total energy is half kxm square. So we can equate this with this half kxm square. Or either in this equation also, if you put x is equals to 0 to find the maximum velocity, so also you get this maximum velocity as under root k by m and xm. And also you can equate this to energy. You can equate the energy at the extreme is equals to energy at some energy at x is equals to 0. So here we are equating energy. This is the energy at equilibrium x equals to, and this is the energy at x is equals to xm, extreme position. So from here we got the maximum speed. So it come out as under root k by m xm. So the variation of kinetic and potential energy and total energy with displacement x are shown in the figure. So we are showing the variation. So at extreme, what happened? At extreme position, the potential energy is zero. Uh, sorry, at extreme position, kinetic energy is zero because velocity is zero at extreme position. And at the equilibrium position, kinetic energy is maximum. So this show the parabolic variation. And the potential energy is opposite to this. At extreme, potential energy is maximum. At equilibrium, it becomes zero. And this shows the total energy. So total energy remain conserved. So this is the conservation of energy in an elastic spring. Okay, so here are some short formulas like Hooke's law. The spring constant k is equals to, then there is the spring potential energy, so it becomes the work done is equals to potential energy is equals to half kx square. Now the units are, you can see the force is Newton, x is meter, potential energy is joule, and force constant k is Newton per meter. Now here some definitions of energy are given that you can read. It is mechanical energy. So sum of kinetic and potential energy in bulk is called mechanical energy. So kinetic energy is due to motion, while potential energy is due to position of configuration. And there is internal energy, which is because of the molecules of the body, internal molecules of the body. So they vibrate with respect to one another. These molecules have kinetic energy due to their motion, and the potential energy due to their attractions and repulsions. So the sum of kinetic energy and potential energy of all the molecules. Okay, so when we do the sum of kinetic and potential energy at molecular level, so that is called as the internal energy of the body at molecular level. So the temperature of the body increases, its internal energy also increases. So internal energy depends on the temperature. Now there is heat or thermal energy. So body possesses heat energy due to the random motion. Due to what? Random motion of its molecules Heat energy is also related to internal energy. It is also related to what? Internal energy of the body. In winters, we generate heat by rubbing our hands against each other. So, in this, the friction energy is getting converted into the heat energy. Then there is chemical energy. So, stable chemical compounding has lesser energy than its constituent atoms. So, the difference being in the arrangement and the motion of electrons in the compound. The difference is called as the chemical energy. The definition you can read. There is electrical energy. It is because of the electrical charges and current that attract or repel each other. So electrons attract or repel each other. So because there is an electric charge is generated, which and because of the motion of this electric charge, the current is generated. So that the exerted force is others. Okay. So the work done on the moving charges with respect to one another. So the energy associated with this work is called as electric or electromagnetic energy. There is one more energy, that is the nuclear energy, that you can read because of the neutrons and protons attract each other strongly distance. So between the nuclei, therefore this uh, nuclear energy will come. Next is the power. So define the term power. What is power? It is scalar or vector quantity. Give its dimension in units. So power is defined as the rate of doing work. Here rate word is added. Energy is what? Energy is capacity of doing work. Power is what? Rate of doing work. So power is related to the time. So if an agent does work W in time t, then its average power is given by. So this formula for average power, which is work per unit time, work by time rate of doing the work. So the short is the time taken by a person or a machine is performing a particular task. The larger is the power of that person or machine. Okay. So as we can see that power and time, they are inversely proportional. Power and time are inversely proportional. If time is less, means the person or machine has more power. If time is more, then it has less power. So we know power is also an scalar quantity because it is the ratio of two scalar quantity. Work is also scalar and time is also. So therefore power is also scalar. Dimension formula you can find ml square t minus 3 unit. So joule per second is called as the watt. It is the unit of power is the watt. Watt is called as. Now if you want to talk about the some biggest unit, then we can use the term kilowatt, or there is a 1 horsepower which is equal to 746 watt. Okay. Now next thing is the determine instantaneous power and express is as the scalar product of the force and velocity. So instantaneous power. So the power of an agent may not be constant during a time interval. As the time changes, so power also changes. So the instantaneous power means for a very small time period. So if we take this delta t and we take the limit of delta t as 0, so this become power at very instantaneous time. So for this small time, the work is also done very small. Therefore, we take delta w with the limit. So this become dw by dt. This is the instantaneous power. Okay, as the limiting value of the average power as the time interval approaches to 0. The delta w is the work done in a small time interval delta t. Then the instantaneous power is given by this. So power as a dot product. So work done by the force is F factor. So for a small distance, let's say dr, we know the small work done is equals to force into a small displacement. So force is this and this is the displacement. So we know power is equals to dw by dt. So if we put this value here, so it got dr by dt, and we know dr by dt is the velocity, is the displacement by time. This is the time. So we know that velocity is equals to dx by dt, or here in place of dx they write dr. So this become dr by dt will become velocity. So we prove that the power is the dot product of force and velocity. So thus power of an agent at instant, so for instantaneous power at any instant is equal to the product of its force and velocity vector at that instant. So it is equal to the product of force and velocity at that instant. Now here, in short, some formulas are given of power. It is work by time, and power at instant power. It is the dot product of force and velocity. If angle is zero, when the theta is zero, and the angle, it is the angle between force and velocity. So unit for power is, we know it is watt, and these are some larger unit like kilowatt or horsepower. So which is equal to 746 watt. Okay. Next topic is the collision. So collision is said to occur between two bodies either if they physically collide against each other or if the path of one is affected by the force exerted by the other. So that is the collision is occur. So for the collision to takes place, the actual physical contact is not necessary. It is not necessary that there is an actual physical contact. If the path is getting affected by if the path of one is affected by the force exerted by the other, if other particle can affect the path of other by applying some force. So in Rutherford's scattering experiment, there is an experiment where the alpha particles get scattered due to the electrostatic repulsion between the alpha particle and the nucleus from a distance So the alpha particle is said to have suffered collision with the nucleus. Alpha particles is said to have suffered some collision with the nucleus. Okay, so the collision between particles are of the following types. So you can read elastic collision are of there are many types like okay. So first is like elastic collision. So if there is no loss of kinetic energy during a collision, it is called an elastic collision. What is elastic collision? When there is no loss of kinetic energy. If kinetic energy loss is not zero, I mean change in kinetic energy is zero, initial is equals to final. So this type of collision is called as the elastic collision. So what is the characteristic? First characteristic is that the momentum is conserved. Second, total energy is conserved. Third, kinetic energy is conserved. Fourth, the force involved during the collision are conservative. Okay, obviously forces will be conservative. Therefore, only the total energy is conserved. The mechanical energy is not converted into, okay, so here the mechanical energy is not converted into any heat, light, or sound. Okay, which means there is no loss of mechanical energy. So the example collision between subatomic particles. Okay, so they are the example of the elastic collision. So the collision between subatomic particles and the collision between glass balls. They are the example of the elastic collision between subatomic particles and between glass balls. Next is there is inelastic collision. Inelastic collision, if there is a loss of kinetic energy, if the kinetic energy getting lost during a collision, it is called as inelastic collision. What are the characteristic? Here also momentum is conserved, total energy is conserved, but the kinetic energy is not conserved. Some of all the forces involved are non-conservative. Okay, so here forces are non-conservative in inelastic collision. Some forces or all the forces are non-conservative. So a part of mechanical energy is converted into heat, light, and sound. So as the total energy is not conserved, so the part is total energy is conserved, but the part of this kinetic energy, loss of kinetic energy. So this is loss is occur because of the heat, light, and sound energy. So example is collision between two vehicles, collision between a ball. Okay. Next thing is we have to show that the total linear momentum is conserved in all the collision. So conservation of linear momentum in collision. So suppose we have two body 1 and 2 that is colliding against each other. So body 1 it is coming from here, it is coming from here, body 1 2, and they are colliding with each other, and they are colliding with each other. So they exert mutually impulsive force. If they collide, if the two body collide, so this body exert force in this direction to this body, and this body exerts force in this direction to this body on the each other during the collision. Okay, for very small time period, when they remain in contact for very small time period, they exerted an impulsive force. So impulsive force is coming for very small instant. So the changes produced in the momenta of other body will be. So this is the linear momentum, like the momenta. So this represented by delta p is for is any small. So is equals to F12. This is the force on one because of this two. Delta t and delta p2 linear momenta is equals to force on two because of one into delta t. So the formula is force into time. So here we okay. So this F12 is the force exerted by body one on body two. F2 is the force exerted by body two on body one. And according to Newton's law, we know if that delta t is same and this force is also equal as per Newton's third law. Thus their signs are opposite. So this linear momenta are equal to each other. So if we multiply delta t on the both the side and if we took this side, so this becomes 0. So from here we can prove that we can write it like this: linear sum of this linear momenta in 1 and 2 also same. So we can say that the sum of change in linear momenta, the sum of linear momenta is not changing, so the change in sum of linear momenta is 0. So which means what? Linear momenta is conserved, the sum of linear momenta is constant. So the linear momenta is conserved during the collision, even though the forces vary in complex manner. During the collision forces vary, but the linear momenta will remain constant or conserved.